Thank you for watching the research videos from the EOG RRC group at the University of Alberta. The objective of the study presented in this video is to screen the effective emulsifier for oil and water emulsions from a broad range of solid nanoparticles. Suitable Pickering emulsifying agents that can render emulsions stable at relevant conditions will be identified. The effects of some physical parameters, such as particle concentration, water-oil ratio, and temperature, that affect emulsion stability will be investigated. Thermal methods for heavy oil recovery have some drawbacks, such as huge heat loss and energy consumption. Chemical-enhanced oil recovery is an alternative method to address these technical and economic issues. The generation of oil in emulsions through alkaline surfactant polymer flooding can help reduce oil viscosity, thus improving the transportability of heavy oil in reservoirs. For the field applications of emulsions, emulsion stability and costs are key issues because emulsions stabilized by surfactants are usually not stable at high temperatures due to the thermal degradation of surfactants. Emulsions stabilized by solid particles are also known as Pickering emulsions. Pickering emulsions are quite stable and can withstand harsh reservoir conditions, meaning high pressure and high temperature, because of high mechanical strength of the solid nanoparticles. In this study, we aim to find effective nanoparticles that can work as emulsifiers for stabilizing heavy oil in water emulsions by adjusting the pH and the salinity conditions of the aqueous phase. Heavy oil from western Saskatchewan was used in all the experiments. 5 nanoparticles, including cellulose nanocrystals, or CNCs, silica, alumina, magnetite, and zirconia, were tested on their capabilities of stabilizing oil in water emulsions through glass vial screening tests under various pH and salinity conditions. All the preceding nanoparticles were provided in powder forms, and the particle size ranged from 10 to 100 nanometers. Nanoparticles were dispersed in aqueous solutions by sonicating for 2 minutes to prevent aggregation. The heavy oil, or mineral oil, was mixed with aqueous solutions of nanoparticles at a specific volume ratio, using a homogenizer to form a Pickering emulsion. Microscopy images of emulsions were recorded with a high-speed CMOS camera to determine the emulsion type. The emulsion stability was evaluated by direct visual inspection of the phase separation at different times through glass vial tests. Emulsion droplet size distribution was calculated by ImageJ software. Various pH conditions were tested for emulsion stability. At pH 3 and pH 11 conditions, CNCs form and stabilize oil and water emulsions, as confirmed by visual inspections of the glass vial and the microscopic observations that less oil and water separated from the emulsion phase compared with other cases. To explain why the CNCs were effective emulsifiers at certain pH conditions, the zeta potential and the Z average diameter of aqueous dispersions were measured. It is shown that the CNC suspension was stable under pH conditions between 3 and 11, because the particle size was similar under all pH conditions tested. The absolute value of the zeta potential was maximum at pH 7. Raising or reducing the pH leads to a decrease in the absolute value of the zeta potential, which makes the CNCs less negatively charged and more neutral wetting, meaning a more stable emulsion is expected. Salinity was set between 2 and 175 millimolar to study the emulsion behavior under relatively broad salinity conditions. Vial images show that adding a small amount of sodium chloride, for example 2 millimolar, helps the CNCs stabilize the oil and water emulsion, and the emulsions were very stable when the sodium chloride concentration was more than 17 millimolar. For the other 4 nanoparticles, it was even harder to mix the heavy oil and the aqueous phase when preparing emulsions by homogenization. And in most, if not all samples, complete phase separation was observed 24 hours after emulsion preparation. The emulsion stabilization mechanisms of CNCs were studied microscopically under both low and relatively high salinity conditions. The low salinity being 17 millimolar sodium chloride, and the high being 175 millimolar sodium chloride. Microscopic images show that at low salinity conditions, some CNC particles were able to adsorb onto the water-oil interface and form a dense layer. At a higher salinity condition, the CNC particles still form dense layers around the droplets, as can be seen in Figure 5b. In addition, the excess CNCs in the continuous water phase formed a network through aggregation due to the weaker zeta potential. When such a continuous phase is in an aqueous phase, as in oil and water emulsions, such network can trap oil and further improve the emulsion stability. The effect of CNC concentration on the emulsion stability was studied to find any possible threshold value. 1% of CNC was required for a stable emulsion at the low salinity condition of 17 millimolars sodium chloride, while 0.5% of CNC was needed at the high salinity condition of 175 millimolars sodium chloride. For a quantitative study of concentration effects, emulsion droplet size distributions with different CNC particle concentrations were obtained using ImageJ software. The distributions show that the droplet diameter decreased with increasing CNC concentrations, and the average droplet diameter becomes almost constant once the CNC concentration exceeded 0.5 weight volume percentage. The effects of the water-oil ratio, or oil content, on the emulsion stability and type were studied. Microscopic images show that the emulsion type was oil and water when the oil content was 0.6 or less, and the oil became the continuous phase when the water-oil ratio was 0.8. This phase inversion, induced by the increase of the dispersed oil phase volume, is called catastrophic inversion, which usually occurs when the dispersed phase volume fraction is near 0.7. Thank you for watching this video. For more research and educational videos, please visit our website at eogrrc.com.